Okay, hello everyone, welcome. I see one person wave, so I guess you can hear me, at least. Yes, two persons, that's good. Welcome everyone to the first GeoDBMS lecture. I hope you can see my shared screen with the PowerPoint presentation. Hopefully the answer is yes. I'm a bit more nervous than you this time. Usually I do it on the automatic pilot this course because I've done it a few years, but now I'm not so experienced yet with doing it with Zoom. So that's a bit exciting for me. So please give me feedback if something doesn't go right, or if you have questions. The chat should be open. By the way, my name is Wilco Kwak, and I'm giving this lecture today. But I'm only giving the first 6 lectures. So the others after 6 lectures, Professor van Oosterom, who is a geodatabase expert, will take over from me, and he will give the rest of the lectures. And for the assignments, we have Liu Hai Cheng, who is going to help. I'm going to be there tomorrow for the first assignment. On next week, or no, it's not tomorrow. It's on Wednesday, and next week on Wednesday I will be there too. And from that moment on, probably Liu Hai Cheng will do it all by himself. But if it's really busy, then I will be there for sure. Okay, welcome all of you. It's really quiet, so I have no idea whether you can hear me. Can one of you try to unmute and talk to us, or?
We can.
Yeah, we can hear you.
Oh, okay, that's good. So the audio is doing fine. Good. So if you have any questions, you may interrupt me. Please do. And for the rest, I'll continue. So I'm Wilco Kwak. I'll be there today. And well, with Zoom lectures, it's a bit tricky. So I think I'm not doing 2 times 45 minutes, but I'm having I'm splitting it in blocks, and a few times we will have a 5-minute break, and then I can have a drink and you can relax a bit, and then after 5 minutes we'll continue. I'm also recording, and so it should be possible to replay the lecture if anybody would be interested in that. And I'm available for questions during the rest of the week. As you will see on the next slide, I think I'm not constantly working at Delft University. So usually I was out of the office all the time, and now everybody is out of the office. So there's no difference anymore, but I'm easily available by mail, Zoom, or any other type of communication, way of communicating. So today, I'll first introduce myself shortly so that you know who is talking and what I know about. Then I'll discuss the lectures of today, or the rest of the course a bit, and then I do this tricky thing. I'll give sort of fast forward version of the lectures of the next 6 weeks. I'll do it in 20 minutes or so, and then you know what's going to happen the rest of the lectures, and then you get the feeling of at least of what is going to happen. But first, I'm Wilco Kwak. I started as a computer scientist. I graduated in computer science on cross-country movement planning. So that's about how to move through the terrain. And you all know about your mobile device is pretty good at route planning. So if you want to go somewhere, it finds the way. And well, usually the algorithm that is used there is that just all the different routes are tried one by one. And that really doesn't work in cross-country movement planning because, well, if you use the road network, you stand at an intersection, you can usually go in 4 directions, But for my graduation project, it was a bit more tricky, because if you stand somewhere in the terrain, you can go in 360 directions. So you have to find a different trick of finding the way, and that's what I graduated on. And that was actually my start on doing stuff with maps, because, well, cross-country movement planning you do on a map, and I really like this mapping part. So that's what I specialized in, basically. So after I graduated, I started to work on the CWI, that's the Mathematics Institute in Amsterdam. And there I worked on MonadDB. At the time it was, well, in 1996, it was the fastest spatial database in the world. And I'm still a bit proud of it. So I was really good at making fast databases. And, well, actually the database was very fast, and I was the one who made the spatial module for it. So that really helped. And but still, so in 1996 we were the fastest, but 1 or 2 months later, some American institute with a really big computer and lots of people, they published an even faster result. But so that was a bit disappointing. But then still, the IDs we had back then in 1996, they were you still see them in current database products. So that's nice. After that, I moved to the Delft University in 2001. So I'm almost working there for 20 years now. And I became a researcher of the GIS technology department. That's where I still am. And there at the GIS technology, I had 2 research topics. One was database performance. Well, I knew that already. And it turned out that database modeling or information modeling became more and more important. And one of the reasons for that is that, well, maybe you've heard of Moore's law. It's a law in computer science saying that basically every year or 1.5 years, computers get twice as fast. So the big problems that I had 20 years ago, they have reduced to almost nothing, because well, the computer is more than 1,000 times faster than it used to be than when I started. So on my mobile phone, now I can just put a whole cadastral database and it fits easily. And I remember back then in 2000 when I started, we had a big project putting all the cadastral parcels of the Netherlands in one mainframe. So database performance still is an issue sometimes, and you will see that. But understanding what the data is about has become more and more important, because, well, computer problems have grown less, and understanding problems, they're here to stay, apparently. And in that role of information modeler, I also started to work at GeoNovum, which is an organization in the Netherlands that try to streamline the spatial data infrastructure of the Netherlands. So they try to make sure that all the government organizations that have spatial data, that if they exchange data between each other, that it fits. That's part of technical issue. What kind of file format are you using? But it's mainly a semantic issue. What does it mean if I send a data set from A to B? Does the person at the other side understand what the data set is about? So that I was doing a lot, and then I decided basically to quit at Delft University, and I did. That was in 2018. Well, I kept this one part-time job for 4 hours in the week, and I did that so I can give this course every year, basically. So I'm only at Delft University for this course, and doing graduation product for students, if there are students that are interested in databases or data modeling. And for the rest of the time, I worked at COPE, which is part of the Ministry of Internal Affairs in the Netherlands, and they're responsible for publishing laws. And well, you might think, what does a computer scientist that likes maps, what does it do at COPE, publishing laws? You have spatial plans in the Netherlands, and a spatial plan is basically, well, you have them all over the world, but a spatial plan is basically a map with rules. And so at scope where they publish laws, they also want to publish spatial plans, and that was a bit tricky. But it turned out well, I liked working at COPE, but there's only people there that work with rules. So our laws, Article 1, Article 2, Article 3, and I was the only expert there that was interested in maps. And well, they liked articles, and I could talk with my colleagues, but not about maps, and I missed that a bit. So in 2020, so 2 months ago, basically, I decided to change back to GeoNovum, and I like it a bit more there, and that's basically because, well, there's Geo in the title of the company, and they do lots of stuff with maps, and I like it. So that's where I'm working now the rest of the weeks, or the rest of the time that I'm not doing education. Okay, first we do some practical affairs, and then we do the fast forward version of the course. I'm not sure about the timing today. I will talk definitely less than 2 hours, but I'm not sure how fast it will be. So we'll see. I'll do the practical affairs, and then we will definitely have a break, which will take, I think, 10 minutes or so for the practical affairs, maybe less. So you have lectures and assignments. Lectures are on Monday, that's today, and on Friday, and then on Wednesday between 1:45 and 4:45 we have the lab, and then we can really meet each other face to face. I'm looking forward to it. So that's the time where we meet, and then there's the weekly deadlines. For Monday morning, there's the reading assignment. So every week you have a reading assignment. It's not graded, but if you read the stuff and you try to answer the questions that are in the reading assignment, it may help you understand the lecture. So this week, I think the reading assignment deadline is right before the lecture on Friday, but the rest of the week it will be Monday morning. It's not graded. It's free to submit your answers, and but if you do, then I will give feedback on it. And the other thing is we have the lab on Wednesdays, and for the lab, you get grades. So it's good to go to the lab and to make the assignments. The lab is on Wednesday, and on Monday, the week after, you have to submit. It's all in Brightspace, so you will find the deadlines there. And we try to grade your assignments within a few days afterwards on Monday. So hopefully on the Wednesday after that, you can get feedback on your assignments. This year we decided that you work in triplets, so teams of 3 persons. The teams are assigned randomly, and for each assignment we will assign new triples, and the idea was that it is nice for you that you have to work with different students every time, and so you meet each other. So that's the plan. I think, and I have to check that Brightspace automatically assigns you already for a team this Wednesday. I didn't check it yet, so I will make a note to see whether you were. And then on Wednesday, or when you work, you can work in teams and submit as a team. Okay, that's it for the practical. Well, that was the start of the practical affairs. We have a book. Actually, I haven't seen anyone buying the book, but I bought it. It's somewhere. I don't see it here, but it's still at Delft University. It's a nice read if you want to know lots of stuff about database systems. It's a nice book to buy, and all the examples that I have are from this book. And so there's a one-to-one match in the SQL part and the book, and that's nice. But then I think I will only discuss 3 chapters of the book, and you can make the exam without buying the book. So most of the time people don't buy it, but if you want to have a look at it, you could borrow it. And well, apparently the book is a 5-part book, and we cover part of the book, part 1, 2, 3, 4, and 5. No, the book has many more parts, I think around 13, so we only do the basics of the book. And the sheets that I will discuss today, and all the sheets will be available on Brightspace. Then there's the final exam, or the final grade. It's 20% of the grades you need for assignments, or you need to do by assignments, and 80% is written exam. And I know that the written exam is not the easiest part. So many people really need the 20% of the assignments, or a nice score on the 20% of assignments to make the exam. So please do your best on the assignments, and that will really help to get your final grade. Okay, no, this was the first 15 minutes. The rest of today, I will do a fast forward version of the lectures. That will be the next half an hour, and after that, I will talk about UML modeling. It's a modeling language, or a unified modeling language, and that is about you need that for the assignment of this Wednesday. So for me, it sounds a bit weird always to start about modeling if you don't know anything about databases. But this UML assignment, you can do it after having heard one lecture. So that's a nice way to start. So I will do the UML modeling after the second break. So it's 14:02 now. We'll have a break till 14:07, and see you then. And I'll keep the chat open, so if you have questions or you want to discuss something, I'll be there. Okay, see you in 5 minutes. I haven't found the chat window yet, so if you're chatting, I haven't seen it yet.
Hi, Vilko. I'm Pratyush here. I had a question about the book.
Yes.
So I tried looking for it and I couldn't find it except on Amazon. And I'm not intending to buy it. So is this the books the same as Fundamentals of Database Systems by the same authors?
I thought that was a different book with similar content. So the content is quite similar. And I haven't really checked where these first 5 parts match with the other book, but so I don't know actually. I do know, I checked, it's a different book, but I did not check whether maybe the first 5 chapters are the same.
Okay, so we'll have to find the similar content material in this book.
You could.
Okay.
Yeah.
Right. Thank you.
Yeah. I found the chat. Okay, time really flies, so the 5 minutes have gone by, apparently. And well, I shared my screen and I was trying to see whether the assignment of triples worked. And it seems that it did. So all of you are now part of a team of 3 for doing your assignment on Wednesday. I saw in the chat another question whether you have to be there on Wednesday. It's not obligatory, but it's highly advised to be there, and I'd like to see your faces. So if you're in the country and you're not too ill or whatever, and I hope to see you. That's it. And the other question on the chat was, how much time do you need for your assignments? Well, you should be able to do it during the contact hours. Well, that was last year, because then we had the whole afternoon for the assignments. But this year, because we only have 2.5 hours on Wednesday, and you need a bit more. So let's say work for the 2 hours or 2.5 hours on Wednesday, and maybe you need, I think you need at least as much time by yourself to finish the assignment. That's about the assignments. Okay, now I'm going to do the really fast forward version of the course. So all the topics that we're going to discuss in the first 6 lectures will be discussed also in the next 10 or 20, no, let's say 20 or 30 minutes. These are basically the teaching objectives of the course. So at the end, you understand what databases are and what the database management system is. You know what schemas are, of database schemas. You know a bit about the database architecture, that it is a free schema architecture. And you know what view independence is and data independence. And one of the most important things is that the assignment is all about is understanding and designing SQL queries. SQL is this sort of programming language for databases, or it's query language. So if you have a database and lots of data in it, then if you want to get the data out, then there is this language called SQL, and it helps you to get from the database the data that you want. And the databases, they look nice. That's point number 5. And under the hood of the database, there is a lot of mathematics, and you don't really need to know all the mathematics, but it helps you in understanding databases. So there will be a lecture on relational theory and relational algebra today, or there will be this lecture on conceptual schemas, UML diagrams. That's more not about the mathematics of the database, but the meaning of the database. And then there's the physical layer, files and indexes, because, well, a database is implemented on a computer, and a computer doesn't work with database tables, it works with files and disks and disk blocks, etc., etc. And most of the time you don't need to know about this, so you just ask your question to the database, and the database takes some time and then comes back with an answer. But in many cases, if it becomes slow, it's really useful to know what happens under the hood of a database. And if you know what's happening there, then you know where to start if you want to make stuff faster, or you know what questions to ask to a database programmer. And what also sometimes happens is that well, you ask the database programmer tries to explain you why a thing you want from the database is not going to work. And if you know what's under the hood, then it's easier to understand these questions. And finally, one of the reasons we have databases is because databases have transactions. And so there will be a bit of explanation on transaction processing. So that will be the fast forward version then. Okay, let's start with the really, really simple database. We have one here. And in this case, the database is just a table, and it has columns and it has rows. And also the table has a name that's useful, and all the columns have a name. So this is basically a database, and this is a database in a relational model, because databases in relational of databases with a relational model, everything in a database is a table basically. And so if you have a relational database, it's all about tables. It's even a bit weird that in a relational database, if you have just one number, then for the database, it's similar to a table with just one row and one column with a number in it. So in relational databases, everything that you see is a relation or a table. And that's really handy or useful because, well, then there's only one thing you can discuss about the database, and that's you discuss tables. And that's really helpful because all the mathematics that behind the database is only mathematics about tables. And then you have this query language, the SQL language. It's a structured query language. And oops, what's happening? And if you use this language and you want from this table, which is basically a database, if you want to have the names of the courses, which have, and the course number of all the courses that have 4 credit hours, you basically send this command to the database. Don't forget the semicolon. It's a computer language, and there you have to be picky about syntax. And well, this query gives what you expect. And as I said, well, it's a relational database, and everything is a relation or a table. So the result of this query is also a table, and you will see that what basically happens is you get a smaller table with 2 columns and 2 rows. And this is the end. This is the result of the query. So that's basically how SQL works. Oh, it's a human. It's a nice language. You can read it as a human. It's perfectly clear what it's saying here, and also for a computer, it's understandable. Of course, it's not that simple. So usually in a database, there's more than one table. So there's lots and lots of tables, and all these tables, they are also related. You cannot see it in this diagram, but if you have a look, that here is the course numbers or the prerequisites of courses, and you see that this number refers again probably to a course in this table. So usually what you can do you see my mouse, by the way?
Yes, yes.
Yeah.
We can see
Okay,
it.
that's good. Fine. That's good to know. Thank you. So if you have this course if you want to know how many hours the prerequisite has of this course, then you go, oh, this course is this prerequisite, and then you go to the other table. Oh, I need 3 credit hours for that. So these tables are linked, and by following the links, then you can make interesting queries about lots of other tables. So that's the SQL language. And now we talk about schemas, intentions, and extensions. So usually if you start a database, you start with an empty database. And when you create an empty database, you basically create a schema. So that's what the database is all about. So in this database, or it's not, it's an empty database, and you have student, and it has names, student numbers, class, major, and we have the course, also lots of attributes, prerequisites, and this is a description of the table, and this is the model of the database, because this tells you already a lot about the database or what data is in it without seeing any example of the data. And so that's a schema. And then if you include the content, that's called the state of the database or the extension of the database. So this is schema, and this is state or extension. And what can you do with the schema? Well, even without looking at the extension, you can see, well, there's no field for address, so apparently it's not an address database, and there's no place for old marks. Let's see here. You have the grade report, you have the student number, the identifier of the section where you can get a grade and a grade. So no, this database does not contain marks, and at most one major per student. How is it? Oh, you see here's the name of the student, there's the student class, and here's, so apparently a student can only major in one course. So that's a bit what happens if you create a database or you design starting making the tables. There's lots of decisions in this thing that that already reflect on what you're going to do with this database. So if it would be the case that you also want to have old marks, then your database should have looked differently. So a schema, by looking at the schema, you can learn a lot about the database. So now I'm going to talk about views and independence. So usually, or basically always, it is the case that you're not alone on working on this database. So there's lots of users, and all these users log into the same database, and they all have a look at the same table. But and I go back to this slide. But most of the time, well, there's different kinds of users. So there might be students that want to look at their own grades, or teachers that want to look at the student grades, or administrator that want to have a look at everything. So each user, and that depends on how you log in, has a different view of the database, because basically a student is allowed to see his or her own grades, but not the grades of the other students. And the teacher is not allowed to see all the grades, but all the grades of the courses he or she gives. So I'm still playing. I'm not allowed to click, apparently. So what happens? All the people that log into the database, they think they're looking at the same database, but they're basically looking at views of the database. So if a student looks at the database or at the table with the grades, the student doesn't see all the grades, but it sees only the grades, and it's still a table where the student can see his or her own grades. So again, all people, they think that they're looking at the same database, and they are looking at the same database, but they all have a different view. Because each of the persons that looks at the database can see a different set of tables, and sometimes a column of the table is not allowed to be seen by everyone, and then you get tables with lesser or few columns. So that's again this nice mathematical part. So also the way all people still see tables, and well, that's nice because tables are simple. So each person, each user has its own derived database, and these are views, and the ID is a view because this person thinks he or she is working on this table, but if you're updating this table, it turns out to be a view because the updates are done on the real central database. So everybody has a view or a subset on the central database, and the view of one person is independent on the view of a different person. And that's nice. And also it's nice that it's all tables, because if now the university wants to switch to a different database system, you only have to migrate the tables and make a new view on the new database system, and without even users that notice it, you can change the underlying database, because most databases these days, they have exactly the same implementation of these tables. So if you do a SQL query on one database, it gives exactly the same result as on another database. Data independence. I was talking about database independence. So what you usually have, you have these users, they think they're working on tables, and these tables are stored on disk. And the database, the user doesn't know or has no idea how it is stored on disk. It only looks at tables, so it's completely independent how it is stored and how the user sees it. But there's one other thing, and that's metadata. So and that's nicely mathematical again. So somewhere in the database, it is stored what tables there are, and also in the database is stored what the names of the columns are, and most of the time also what the type of the columns are. And that again is the intention of the database. And where do we store it? And not in a separate system, but again in the database. So the way the tables are structured is again itself stored in a table. So the database that we saw before with students and courses and sections is the meta model, or the way how the database is described is stored in these two columns. So here it says, well, we have a student table, and the student table has 4 columns. And here that is linked to this columns table. Here we see 4 columns. Apparently, there's a column name, there's a column student number, a column class, and a column major. And so these two tables exactly describe what is in the database. And again, it is the database itself, and it's stored inside the database. That's a bit tricky, but it really helps. So even if you want to query, if you want to know how many columns are there in the student relation, then you can do that with a SQL query. So everything is tables and queries in databases, and it's really convenient. And not only the model is stored in the database, but also the underlying file structure, because databases, they are only tables, but in the end, if you implement a database, usually you store it in a file. And a file is just a bunch of characters most of the time stored on a disk. And now if you have a student database, how would you store it on a file? Well, you could say, well, I know that I'm going to store all the student information in a file. I'll put the name first. A name is at most 30 characters. So the first byte till the byte number 30, there I store the name. And then at byte number 31 in the table, I start with the student number. I use 4 bytes for that. So then I end up at byte number 34. Then the class. I only need 1 character for that, so that's easy. And the major, it's a code of 4 characters. So this basically describes the file format in which the data is stored on disk. So for each student, you need 40 bytes. And then if you want to know data about student 2, you should open the file and then first skip the 40 bytes, and then you get the next student and read. And then that's where the name of the second student starts. So this is kind of nice, because now you have a mapping from a really nicely well-structured data thing with tables and columns, etc. And with this table, you can translate this to bytes on a disk. So here you go really fast from a high modeling language to bits and bytes on disk, and that helps you in understanding what's happening under the hood. And this is really the way. Usually it's a bit more tricky, but this is really the way how databases are implemented. Let's continue. Well, let's revisit the notion of a database. It's a bit tricky because there's these 2 words, and one is database and one is database management system. And most of the time people mix these 2, and usually if you say database, you mean the data plus the database management system, and not only the data. So if I say I have a database of all the Dutch cadastre, well, usually you don't say that. Then you usually say I have a data set of the whole cadastre. If you use the database, you also include the management system. So please only use the word database if you include the management system as well. I do this point number 3, and then we'll have a 5-minute break again because I need to have a drink. It's water, don't worry. Database architecture, 3 schema architecture, view and data independence. I think I already discussed this. So what's the 3 schema architecture? Well, the idea is that databases are so big and complex these days that you cannot manage it all in one. It's not one person that manages it. So different people are responsible for different stuff. So there's this database computer managers that discuss the internal schema. And on top of this internal schema, you have a conceptual schema, which is a bit more complicated. And the end users, they see the external views. And in most databases, you see this. So it's basically, it's all tables. But these are the external tables, the conceptual tables, and the internal schema that contains lots of stuff like indexing, and this table is sorted on this, or this table has the spatial data in it, and we have to handle it differently. So in many systems, you see these 3 levels: internal, conceptual, and external. So it's important to know these terms. Okay, it's 14:30. Let's have a 5-minute break again, 14 till 14:35. Okay, see you in 5 minutes. I think I should have muted it. Okay, it's 14:35 again. I continue. I have one more message for you. I have a dog, and I'm working at home, as all of you are, I guess. And usually it's no problem, and the dog is sleeping somewhere behind me. But if the doorbell rings, the dog starts to bark, and I will introduce a 5-minute break then if the doorbell rings. So whenever that happens and you hear the dog bark, I will run downstairs, open the door, get the package. I'm not expecting any deliveries, and run back up, and that will take about 5 minutes. But the dog is really loud, and usually I cannot talk anymore if the dog is around. So now you know what's going to happen then. Hopefully it will not happen at all. So relational theory and relational algebra. That's about the mathematics that is behind the whole thing. Let's discuss. Have a look again. So again, we have this thing, a database. It's lots of tables, and there's metadata. These are tables, and there's data. These are tables. And there's users looking at tables. And under the hood, what does it mean when you have a table? Is it okay to have two rows with exactly the same value? Can a row be empty? What happens if you combine two tables? And for that, you have a thing called relational algebra. And here you can see all these weirdo signs that you may know from mathematics. Well, yes, it's this relational algebra is mathematics, but don't be worried. It is not that hard. So if you discuss relational algebra, it turns out that, like with normal algebra, when you can add two numbers or multiply two numbers, there's behind a database, there's this relational algebra, and it's similar like normal algebra is with numbers, and relational algebra is with relations. So it tells how you can combine two tables, how to calculate the difference between two tables. And the nice part is that, so if you have a SQL query, then what under the hood happens is that the SQL query gets translated to a set of these relational algebra formulas, and that is what is implemented. And the nice part about mathematics is that it is all very well defined. So you know, if you do a query on a database, you know what to expect and how it will be implemented. And well, that's convenient. So this mathematics behind the database it's convenient. So again, I said already this. So the semantics operation, always SQL queries, they work on tables, and it's always table in, table out. So for example, what you do here, what you see here, again, you have this query when you get the course name and the course number from the courses with credit hours is 4. And you go table in and table out. And what happens is, this is what the table that gets out. What basically is done is you have the select part where you select only course name and course number. What happens is that these other two columns, they are thrown away, and the where part, credit hours equals 4. That means this row and this row is removed, and then you end up with basically this part of the table. That's what you see over here. So that's the nice part of semantics. And what you will learn is that these semantic operations can be expressed in elementary operations on the table. So this is a select. Here you see a weird sigma sign. This is part of the relational algebra. And this is one of the operation, and the other operation is this. And then if you do both of them, then you get this. So so this is the relational algebra statement that belongs to this SQL query. So that's what's happening under the hood. And well, that's convenient because that helps with understanding exactly what it does, a query. And well, yes, we repeat that. It doesn't depend on the meaning of SQL. It doesn't depend on implementation. It depends, and you can prove that it is correct. And the meaning of operations is mathematical functions. And there's this one thing that I didn't really discuss, but the SQL language, it is a declarative language, and that means that you say what you want, and you do not say how you want it. Let's go back to this slide. So here, this query. You see that you say what you want. You want this course and this course numbers from this table with courses, and but this query doesn't say how it is implemented. Well, in this case, it doesn't really matter. You have a table with only four entries, so it doesn't really matter how you do it. But if you have a database with millions of entries and you want to find all the entries where credit hours are for, there are different ways of doing it. You could sort the table on credit hours and then only look at the specific part of the table. So that's one solution, doing a sorting first and then figure out in which part of the table to look. But the other thing you could do is just go through all the rows of the table and just print the ones where credit hours equals 4. And for simple queries, it's most of the time straightforward. But for complicated queries, it's a bit more tricky. So the SQL language, and that's what the declarative is. You say how you want it, and not how you want the computer to calculate it. So you leave that to the computer. So if you send a really complicated query to the computer, and then what the computer does first, or the database management system, what it does first is doing query optimization. So it thinks, oh, if I want to get this data, what should I do first? Should I first check all the students, whether the name is this, or should I look at the grades? And that is not specified by the language. So language only says what you want and not how you want it. Okay, now we go to conceptual schema languages. This is, again, here you have the thing again, you have the users, the metadata, the data, and the relational algebra. And but it turns out that not many people, they think in tables, they think in different objects. Like if you want to understand the database, you talk about persons and courses, etc., and not really about tables. So there is this language, it's called UML, and it's a modeling language, and it describes the things you talk about in a way that it's easily understandable by humans. So it's called UML diagrams, and I'm going to show a lot of them, and you're going to make them on Wednesday. And this is about describing what's inside the database without using the weirdo vocabulary that belongs with databases. So UML diagrams are, I use them a lot. I'm a proficient UML modeler, and it happens a lot that I go to an organization and then we discuss, okay, what kind of data do you have? And then this data expert comes and they talk and talk and talk and talk. And then in the end, I have to make a diagram out of this. And that's usually, if you start to make a database out of something, that's the first thing to happen. So you talk with an expert, and there's also always fuzzy stories these experts have because they don't know what's important and what's not important. They have their own jargon, and then in the end you have to make a database. And what I usually do is make this UML diagram. And you will see also in the assignments that you get, you have to make a UML diagram, and you have to make a UML diagram of a part of the world. And the text that you get, it's really fuzzy, and there's a lot of words that you don't understand, and that doesn't really matter, but still you have to make a UML diagram. So that's your assignment for Wednesday. So and that also means that there is not one correct answer, but there's more of them. So please go ahead on Wednesday and have fun. This is basically of the course that we saw before. This is a UML diagram of the world that we have, and it is quite similar to a database tables, but it helps a bit. Here you see that there are students, they have classes, majors, and a name, and there are sections, and they have an instruction, a semester, and a year. And that's a nice part about UML. They are related. So here you have a student, and here this word is important. It belongs to the arrow. The student takes a section, and a section consists of courses. And a course, and that's interesting, it is related basically to itself, has, well, not to itself, but to other courses. A course has other courses as a prerequisite. So these diagrams, they are really useful in discussing what's inside the database, and they're also quite simple. So even if you're not an expert, you basically can understand what's the meaning of these diagrams. And well, of course, in real life, these diagrams become a bit more complicated. So this one it's hardly readable, but this is another UML diagram, and this one is really from the real world. And I think if you are going to do this Geo 1008 course, geodatasets, this UML diagram might be discussed over there. So that was UML diagrams, and the nice part is that so a UML diagram discusses things in readable terms. So you can make an UML diagram, but it's also usually, if you have a UML diagram, and that's called the model-driven approach. If you make the UML diagram in the right way, you can push a button, and then the UML diagram gets automatically converted into a database schema. That helps you, because then you do not have to learn this language or this part of SQL to create tables, etc. Because, well, you make this nice diagram and you push the button and you get the schema. And the tool that you're going to use or that you could use for making UML diagrams is somewhere hidden, and it's really hard to find this button, but there is a button to go from UML to a database schema. So if you want, you can try this at home. Okay, a bit about the physical layer and transactions, and then we will start with the UML modeling. I think I'll do this physical layer part a bit quick because I'm a bit slower. I thought I would be faster via Zoom, but I'm slower via Zoom, so I have to be. I will go a bit quicker. So physical layer. So this whole database is implemented on files and indices, and there's a lot of stuff to be done. So you have your image again, and these tables, they need to be implemented on this. And I'm not sure whether you know what this is, a disk. And it used to be the case that hard drives looked like this. So it's you have these devices, and you have a magnetic layer, and these rotate, and you have a read and write head, and you have arms. And so if you do a query on a database, in the end, it will result in parts of this magnetic disk to be read by this read-write device. And now I have to check whether what the next slide is, because no, there's no next slide. So, and Moore's law that we discussed before is interesting, because all parts of computer science has become much faster. So these disks has become more dense, the CPU has become faster, these cables which transfer the data have become faster. But there's one thing that has not become faster, and that's the rotation speed of the disks. So these disks, they rotate really fast, but compared to the rest of a computer, not so fast. And that means that if your data is on this disk, and you see the arrow that it rotates this way, if the data that you want is here, and you want to read it, then you basically have to wait till the disk rotates, and compared to the speed of a CPU, this rotation is really fast. So all the time that you need to rotate this disk, the computer can do millions and millions of calculations. So and basically the problem is, so if you want to have a fast database, it's always the rotating disk that is the bottleneck. And what computers are, and if you do databases, basically what you do is try to optimize to make sure that you do not need to wait for this disk rotation. And there's many different tricks for that. So you can load all of your stuff into memory before, or put all the stuff that you need together on the same disk block, so that if you need 5 objects and they're close together, you get them in one go instead of having to wait 5 times. So a big part of databases is about disk optimization. And then, answer could be, well, these days you have these solid state disks. They have no rotating part anymore. And yes, that's really true. With these modern solid state disks, the database world has really changed, and there's many databases now that do not have rotating disks anymore. But the real big databases, somehow they still run on rotating disks, and for the real big database, you still need to optimize disk block stuff, etc. So that's what's discussed. A table is implemented as a file. So here you see a table, and here you see part of the file, the numbers, and then it turns out, or it is the case, that this file is stored on disk blocks, because usually if you have a disk, you split, you have blocks of 1 kilobyte, and if you read a block, or if you read part of the database, then you read one block and another block, and that's where the bottleneck is. So if you want to know how long a query is going to take, it doesn't matter how much data it is. You only have to count the number of blocks that you need, because, well, that's what you're waiting for, disk blocks. And that's interesting because, well, let's see what happens if you have this query, find all the parts of the database where the number is 25. Oh, no, then you would start here. Let's see, the first disk block. Well, it's not there. 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 Okay, what happens? So you've read six disk blocks, and then you turned out there's no data. So you could do that a bit more efficiently, and that would be by sorting. So it would be nice if this data set could be sorted on this table, because then you could easily search and you don't have to have a look at all the disk blocks, but then you can start in the middle and see, oh, my number is bigger, so I go this way, etc. So sorting really helps. But then you can solely sort on one field, and then if you want to search on a different field, you're back in trouble again. And that's what the database is all about. There's all these different kinds of tricks to do the sorting, and that's what's making expensive databases expensive, because they are just better at doing the sorting for you. We discussed this. So you have these days, you have solid state disks, no rotating devices anymore. It's really different. And an index. So if you have here the table and it's not sorted on this field, but still you want to query it on this field, then you make an index. And basically that means you make a copy of the table, or you make a copy of a part of the table, and you sort on that. So here, I guess this table is sorted on a column that you do not see, and then you create an index, and this index you sort on this attribute, and then on this index you can search. Well, if you want to have number 25, well, you start in the middle, called binary search. Oh no, 25 is not here. Let's try here. No, it's still bigger. Oh, 25 is not here at all. But if there is a number that you know where to find, like number 10, then here in this index you have a pointer to exactly the place on disk where you need to go to find that number. So what usually happens in databases is you have a table, and there's one attribute that you store it on, and you sort it on. And if you want to search on different properties, then you get indexes. Okay, one final thing before we have the final break, and that's transaction processing, because, well, these databases are expensive. Things for two reasons. One is that because, well, they're really good at this optimizing this underlying disk, and the other thing is, well, databases are used for transactions. And what's a transaction? Well, all users, they think they are working on the same database, and that's the case. But what happens if two users are updating the same database? And well, what could happen, for example, if you have a database for your bank account, and then what happens is, if you want to withdraw money from your bank account, what happens in the database is, go to the ATM, and the ATM, well, basically looks at your bank account or how much money there is, and checks whether there's enough, and then it checks how much money is there. Let's say that 1,000 euros, and you withdraw 50 euros. Then it says, oh, there was 1,000 euros. I remove 50 euros. Then we get back 950 euros, and that's what's reinserted in the database. So, but what happens if someone else, for your employer, for example, just is paying you money, and it's looking at the same database, and it sees, well, how much money is there? 1,000 euro. I'm going to pay this person 200 euros of salary, and that will result in a new bank account value of 1,200. So things like this happen, and both persons, they have the idea that they're the only one in the database. But then, and let's see where this slide is. So there's basically two operations, and they operate on the same database, and they read items and write items. And now, if you do it in the wrong order, then you get into trouble. So maybe after the person is doing these two transactions, 50 euros withdrawal and 200 euros salary, you're supposed to end up at 1,150 euros. But if you implement it the wrong way, it might be that you have this lost rights problem, that one of the rights is wrong. So what the database usually does is, if there's more than one user, and if all the users are reading, it's not a problem. But if users are writing database tables, then it's keeping track of who is reading what and who is writing what. And then if two persons are writing to the same table, this table gets locked for one of them. So then the database is making sure that each person, that these lost rights do not happen. And, well, that's the other reason why databases are important, to keep stuff synchronized. Here you have the last update problem. And this is a word you basically need to know. It's called this asset thing. And this asset is what makes databases expensive or interesting. So if you have a database, you can be sure that it is atomic, consistent, isolated, and durable. And that basically means that this durability means that, well, if you stop the database and continue a few days later, your data is still there. And this isolation is about that you all, if there are multiple users, that they all have the idea that they're working on on their own. So there's no interaction between the user or the different users of the database. Consistency is about keeping the data sets consistent. So if you have a table with prerequisites and it should point to a course, and you remove the course, then the database is going to say, oh, this is not right, because now I have a course with the prerequisite that doesn't exist anymore. And this final one is atomicity. It's about atomic transactions, and that's the other nice part of databases. Sometimes what you wish is that if you do two things on a database, you want both of them to happen or none of them. It should never be the case that one of the two happens. And let's take an example. If you start traveling, for example, if you go to somewhere else, you want to book a flight, and you want to book a hotel. And what you usually want is, you choose a bit, and you say this flight, and then on this day, then you should also book a hotel on that day, not a day later. And somehow what you always want is, but you never know for sure that if you book a flight, that hotel still will be there. So theoretically, what you want is it's called an atomic transaction. So if you want to book them, you want either both the flight and the hotel to be booked, or none at all, none of them. And that's what databases are good at. So databases have this thing called a transaction. And if you use them, then you can be sure that either none or all of them happen. Like an atom, it's indivisible. And so if you want that, so if you want to do two operations on the database in an atomic way, you say, well, I want to start a transaction now, and now I do all my operations on the database, and then you enter transaction. And then the computer is going to make sure that all the things between the start of the transaction and the end of the transaction only happen once or not never. So, and that really works. So if you have a database and you start a transaction, and the database is working on the transaction, and if you pull the plug halfway, so then in the end, if the database gets restarted, so you then it's going to have a look at the state and see, oh, so I was halfway during a transaction, and then it has a transaction log. And then it decides, shall I continue this transaction and finish it, or roll it back? So, and if you roll it back, then this whole transaction never happened. So it's either the case that you do not book the hotel and you do not book the flight, or both of them happen. And it sounds easy, but it's really tricky, because as Murphy's law says, problems always happen. And so what happens if you have a transaction, and if you're trying to roll back a transaction, you were halfway and you pull the plug again, then it becomes really tricky. And that's where databases help you. So if you are in an environment where transactions are important, that's one of these cases when you have to consider a database. That's basically it. So Murphy's law, we discussed. Concurrency control, discussed. Okay, that's it. So it's 15:03. At 15:08, I will start again, and then we discuss UML modeling. And if it's okay, at the end of that, I think this will be one big block, or maybe with a 5-minute break again. And at the end, you should be able to do your assignments. So it's 15:04. So see you each other at 15:09. Right, I'm ready. Okay, it's 15:09 again. We had the fast forward part of the course, and now we're going to do it at normal speed. So one of the things we discussed before the last break was UML modeling, and now I'm going to give you a sort of course into explaining how this UML modeling works. And I'm reusing slides from Professor van Oosterom, and he was reusing them again from the University of Amsterdam and the European Community Joint Research Center, because they've made this really big UML models called the Inspire model, and it's a big European project. And also for standardization of spatial data, for standardization of polygons, and what a point is and a multi-point, etc. There's this ISO committee, it's called ISO TC211. They were also using UML diagrams. So in lots of places of the geo world it's used, and we are reusing those slides. Actually, this UML language was invented by these three guys who were using lots and lots of modeling languages, and they were all different. And then they decided to have a universal modeling language, also known as UML. And I'm teaching that, and I'm teaching just about enough to give you the basis to read these ISO standards and to read these Inspire UML diagrams. And this, and at the end of the course, you will know what a class is, an attribute, an operation, an association, a constraint, package, stereotype, all those kinds of words. And actually, the UML standard is lots bigger, and it has several types of diagrams. So you have also the use case diagram, where you describe a use case where a patient is making an appointment with the scheduler, and then the appointment gets scheduled, etc. And this is also a UML diagram, but not a class diagram. And today we're only discussing class diagrams. So also interesting use case diagrams, but outside the scope today. And this is this is a serious UML diagram. It's not so readable because of the letters, but for the rest, at the end of the course, you could understand all the letters that are in this diagram. And this one is about it's from the Inspire set, and this Inspire project is a European project where in Brussels they said, well, we need to have all this data from all the member states about the environment, and actually we want from all the member states, we want exactly the same data. So, and that's important because before that they asked also about the same data, but it always went wrong, and it went wrong in different places because well, one of the things they wanted to know is how much forest you have in a country, and it turns out that if you look at the map of Portugal, that's south of Europe, and it's a bit hot, and they have not that many trees. So if there's a few trees there, they're really proud of it and call it a forest. And in other member states, Finland, it's completely covered with forests. And what happens is that on the topographic maps of Finland, if it's forest, they leave it white. So in Finland, the default value of a map is forest. So if both of them send their topographic maps to Brussels, then you might conclude that there's more forests in Portugal than there are in Finland. You don't want that. So it's really important to do the standardization or to harmonize those data sets. And I'm not sure that UML really helps for this example, but UML can be used as a tool to make sure that you can also put all your definitions in your UML diagram. You can make sure that you use the same values. And so for that project, the Inspire project in Brussels, there were teams that for many themes data specifications were made, and the member states had to provide data according to the data specification. I was also involved. So if there's one of the themes was land use, it's about how people use the land, and planned use, how people plan to use the land. So it's about spatial planning, and I made the UML diagram for that one. I was the technical person there, so I draw the diagram, and I was not really involved about the real meaning of spatial planning. So I'm not a spatial planner, but I learned a lot there, and I learned how useful UML diagrams is, of making UML diagrams. So we start with UML diagrams, and there's one thing that you need to know. UML is an object-oriented modeling language. It's all about objects or classes, and that's an interesting difference because a class is a set of objects with similar properties. So if you look outside, or if I look outside, I see cars, and there you have again. So a car is a class. So And then if I look at the individual car outside, that's an object. So that's the difference between cars and between object and classes. And most people confuse these two, and it's perfectly legal to confuse them. And people do it all the time. But sometimes it's really to understand. Sometimes it's useful to be able to distinguish between the class of cars and an object car. And so be careful if you use the word object, that it has two meanings. And for the rest, use class if you have the possibility. Okay, well, then the other thing about object orientation is in object-oriented modeling, you assume every object has identity. And we'll see that in the next diagram that usually in databases you have to create a property or an attribute like a student number or a license number of the car to make objects unique. In object-oriented modeling, you assume that there is such an attribute, and you do not always put it in the diagram. So let's see it. Well, here you have the most simple version of a UML diagram. It's just a rectangle with the word in it. And let's go to the example. And the word is the name of the class. So if you would put the word car here, then you would have a class with of cars, and that would be your model. And then you basically say, well, we're living in a world where we discuss cars. And usually that's not enough, so you're going to extend the model, and that's what you see over here. We have a class car, and that's a rectangle, and then you put a horizontal line there, and under the first horizontal line, that you get attributes. So here you see a car has a number of seats, and this attribute is called seat number, and it is an integer. So it means a number bigger than 0, or 0 or bigger. And also, apparently, in this case, or in this database, or in this model, the color of the car is also important. And it's really important because, well, apparently it's even important if a car has more than one color, that you can specify it. So in this model, a car has one or more colors. So this is how you talk about this UML diagram. So we have cars, and they have a seed number that's a number, and color more than one. And then there's another horizontal line, and then you have operations. And operations you can recognize by these brackets. And these are properties, and these are things that you can do with the car. And they usually change the state of the car. So if you have a car, you can do an operation on it, like repair the car. And between the brackets, you have stuff that you need to repair the car. So you need a tool. And the end result of this operation is that a bill is something happens with the bill. And it's not specified what's going to happen, but the end result is a bill. And the other thing you can see, well, there's another thing you can do with the car. Is you can wash the car. You don't need any tools for this, apparently. And the end result, it says void. That means that apparently there's no bill here, but void means that something is happening to the internal state of the car. So if in this system you use the operation wash, something happens with the car, and you cannot see it at the outside. So actually, if there should have been, if there would have been an extra attribute clean, and it would have the value false or true, then if you do the wash thing, an end result would be that the attribute clean would be true. So, but what you basically need to remember is this is simple UML diagram. You have rectangle attributes of the name of the class is here. Then you get the attributes, those properties, and then you have operations. And actually, because this Inspire project is all about exchanging data sets, and this is data, and this is no data, these are operations. In these Inspire UML diagrams, you will not see any operations, you only will see attributes. So this is not too much discussed further on. Again, a bit more formal, the class name, attributes name, operations name, and operations have parameters, there's data type there, and there's also output data type. That's it. And then these class, they have attributes. I'll show it again here. Here you have the attribute name and the data type, and there's a bit more over there. I'll go forward again. An attribute is a characteristic common to all objects of a class. So if you discuss a car, well, all cars have wheels, so an attribute could be the number of wheels or the type of wheels. And if you have an attribute, you always you have to do some specification. Attribute belongs to a class. The attribute has a name. The attribute has admissible values or a type of string. And sometimes you see a default value like this. And for example, all these things together, here you have the attributes to a class student, saying, well, attribute lives in a city and that's of type string, and the value, the default value is The Hague. So this you sometimes see in UML diagrams. And what you also see is a multiplicity and a visibility. And this visibility, you see in front of the attributes, you see a plus or you see a minus. And that basically means who is allowed to see that value when you have only two values. So it's public, so everybody is allowed to see it, or it's private, and then you're only the rest of the world is not allowed to see that. And this is not used in Inspire because Inspire is about open data, so everything is public, but this public and private is more often used in programming languages, so like Python, where in Python you also have attributes, and in Python I think attributes also can be private or public, but here in Inspire we are not using it. Then there's the multiplicity. It's the number of allowed values, and you put it between these rectangular brackets after the attribute. So for well, let's go back to the example here. Here you have the attribute color. This means this is called the cardinality. So a car has one or more colors. And sometimes it also states 0 here. Then you could have cars without colors, and that's an optional attribute. That's multiplicity, and then you have a possible default value. So same holds for operations again. So the operations have a name. They can be public or private, and they have parameters and an output type, and all this is defining the operation. So that was basically UML with diagrams with one class, and that's okay. But it becomes nice when you combine attributes or you have different classes and they are related. And so, as discussed in UML diagrams, classes are rectangles, and then if there are relations between the rectangles, they are drawn by lines. And this can be dashed lines or dotted lines or arrows. There are many different kinds of lines, and most of the lines, they are between two classes. Like a car usually has an owner, and then you have two classes, person and car, and you draw a line between them saying ownership. That's called a binary relationship. And sometimes they are directional, so then you have an arrow at one at the end. And in some really specific cases, you have a relationship between more than two classes. And this, I never use them in all these years that I've been modeling, but they do exist, and it's up to you to find examples. And it's even possible to have associations between more than 3 classes, but that's really rare. If you know one, put them on the chat. It's nice to think about it anyway. So how does it look, these associations? Again, I start with the example, and then after the example, I put some keywords there. So here you have a class company, and you have a class person, and you draw a line between them. And this is standard UML, and there's 3 places at the line. You could put a word at one endpoint. You could put a word at the other endpoint, and you could put a word in the middle, and then there is the cardinalities. And how should you read this? Well, basically, you say, well, you have companies and persons, and if you use this word, you say, well, there's an employment relationship between a company and a person. And then how do you read it? Well, like this: a company, and that's basically always works. A company, and then you go to the end of the relationship, employs 1 or more persons. So that's how you can read it. And so if you read the text and you see a company employs 1 or more persons, then you can easily make a UML diagram. And the other way around, a person works at 0 or more companies. So this is an interesting database because this is a database where people can be unemployed. And so this is what modeling is about. And I remember from this time that I was doing the Inspire modeling, all these values, like should this be 1 or 2 or 0, they were discussed extensively, and these values are really important, and it's always nice to take the time to figure out what numbers there should be there. So you saw this UML diagram in the beginning. It fits in one slide, but I think it was discussed by, I think, at least 50 people for days. So each letter, it was discussed by lots of people and extensively. So these UML diagrams contain lots of information. Another thing here, this is a bit weird. You have an individual, and that's related to itself. Well, that doesn't mean that here you have the parent relationship, that you are your own parent, but an instance of the class individual is related to another instance of the class individual. And well, you can read it again. Individual has 2 parents, and the other way around, if you read the arrow, or the relationship, individual has 0 or more children. Oh, that's well, this is a sort of realistic UML diagram. So this is how you do the modeling. So again, a line between 2 classes is called an association, and it defines the relationship between 2 classes. It has a name and the things at the end called role. So this is the role of B for class A, and this is the role for class A, etc. And here again, we have the example. So, well, this is basically it, UML diagramming. But then it turns out there are a few kinds of relationships that are really important. So we have invented different kinds of arrows for them. Let's have a look at them. Oh, first discuss multiplicity. Well, you see all these numbers there, and this number means the number of instances that may be associated with the class. So in most of the time there was a 1 or a 2 or a star, or here you mean several. 0 or 1 it means. And in really rare cases you have 0, 2, 4. That maybe happen with a car that can have 4 or 6 wheels or so, but it usually doesn't happen. So most of the time it's 1, it's star, or 0, or optional. Okay, that's about multiplicity. And then there are some associations that have a special meaning. So the one we saw before is a neutral, and then you have to look at the name of the association to understand what it's doing. But some come with predefined semantics, and the important ones are generalization, and that has, then you have an arrow or line that means is a, or aggregation, that's part of. Let's see where we start with generalization or inheritance. And that's really nice because it happens a lot that you look outside and you see, I don't only see cars, but I see only also bicycles or buses. And then you say, well, all these things have things in common, but not everything. So what you do is you make one superclass, and in this case it's called vehicle, and there you put the attributes of that all the things have in common, and then you make, in this case, 3 subclasses. So you have car, boat, and buses, and then you say a boat has extra properties like a draft, and a bus has extra properties like the number of passengers. And you should basically read it as this: a bus is a vehicle. So if you're going to make a UML diagram and you read somewhere the word is a, that's a sort of trigger saying, oh, is a, maybe I should use inheritance. And you can also say that you can do without inheritance or without generalization, because this is a arrow is just a shortcut of saying, well, a bus has this attribute, but it also has this and this attribute. So instead of using inheritance, I could have copied these 2 properties to this, and this object, and then I would have one fewer class. But still, it helps in many cases to use this inheritance, and it makes the models better understandable. Sometimes I look at your questions, and I don't know when the questions were asked, but one of the questions in the chat was the diagram seemed too similar to classes and class methods in Python. Yes, that's really true. And what happens a lot, or what you could do, and what happens a lot, is if you want to make a Python program, you start with making a UML model, and then you could push a button and you create a database table, and you could push a button and you have the start of your Python program. And so UML describes what operations there are in your Python program, but not implementing them. So UML is a modeling language, and then you could implement the model in Python, or you could implement the model in a database. And if you use the same UML diagram for your database and for your Python program, that really helps, because then you know that the 2 are synchronized in a way. And I see another question. How can we imagine the contents of the operations? Are they functions with SQL code? Yes, it could be, but well, yeah. But these operations, they match more with Python than with SQL, but you could implement operations in SQL, yes. Okay, I'll continue. So this was inheritance generalization. So the purpose of this subclass and superclass or inheritance thing is sharing similarities while preserving the difference. It's an association, and one class is a superclass, and one or more classes is the subclass. Superclasses show the features that the subclass is in common, and each subclass inherits the attributes. So here you have it again. Subclass, superclass, it's called, all these words are mixed by all people that are using UML modeling, so you should know all of them. Subclass, superclass, inheritance, generalization, and this one is more specific than this one. And yes, so that's basically it. So that's about subclasses and superclasses. One final thing I think that's in this one. Sometimes, and you do not really see this, or it's really tricky. But if you look carefully, this word vehicle you see in it's in italics, and that means that it's an abstract class. And what would that mean? You cannot see it in the UML model, but if you have a database with, according to this model, in this database there will be cars, there will be boats, and there will be buses, but no vehicles. So and that's so vehicles don't exist because this vehicle, it's an abstract class. It's not to be implemented in a database, but this vehicle class is just meant to put the shared attributes of cars, boats, and buses there. So that happens sometimes in the Inspire project, and you get you have this nice UML diagram, and right in the middle of the diagram there's this word vehicle, and then you get the data set, and people say, that's weird, I have this data set, Inspire data set, and it doesn't contain vehicles. Yes, and then I have to explain, well, look really carefully, this is in italics, and it means it's an abstract class, and that doesn't mean that they're not there in reality. So I quit using it, or whenever I use an abstract class, I put a note there saying, well, watch out, this is an abstract class. So be careful if you see them, then you at least know what it is, an abstract class. Okay, well, there's two more special types of associations to discuss. There's aggregation. And what's the definition of aggregation? It is between two classes, between one class and several instances of the other. And let's have a look at an example. Let's have regions and countries, and you have a region belongs to one country, and a country can have star, which means 0 or more regions. So this is also how you read aggregation. So if you see in a text you see the word is a, then you know that's inheritance. But then if you see in a text you see has a, then you know I should use aggregation. And so this read, a country has 0 or more regions. And the difference between the other arrow is that you have one of these diamonds at the end, and that means a country is an aggregation of regions. So that's the other kind of diagram or the arrow you use a lot. And actually of this aggregation, that there are two types, and the other one, they're really similar, only the diamond is black. And it's called a composition relation, and it's almost the same, but in the one case, you say, well, the one cannot exist without the other. Like a book consists of 2 or more pages, and if you throw away, or if you start to work with the individual pages of the book, then the book becomes useless. So book and a page, they always go together. And as another example, I have a computer system here, I have a laptop, I have a screen, I have a printer here, and that is not a composition, because if I unplug the printer from my system, it's still a valid printer. So all by itself, the object is still useful. And if you use the composition relationship, you basically say, well, the object by itself is not so useful. It's only useful in the context of this composition. But it's really it really depends on the application, and it's not always so clear which one to use. And don't worry about it, because it's not really important. Well, what usually happens when you start doing the assignment, then you discuss for hours, oh, it should be this aggregation or composition, and in most cases it doesn't really matter. I see a question again. Is an abstract class the same thing as an interface? No. And I'm not going to discuss interfaces, so I have to check it again in the documentation. So I cannot explain exactly what the difference is. We could discuss this on Wednesday if you want. Okay, then there is other type of arrow that you sometimes see. It's called, this is a real arrow, it's called a navigability arrow, and it indicates the navigation supported by an association. It's a sort of hint. So if you have two classes, A and B, and you put an arrow this way, that means that the computer system that is behind this thing will usually have questions like, find me all suppliers that belong to this class, and not the other way around. So so this is a sort of hint to the implementer in which way this relationship is going to be used. And then if you create a SQL database for it, then you know where to put indexes, etc. But it has no real meaning, or that's the meaning of this arrow, and it's only a hint. So not very often these arrows are used, but you still sometimes see them. Then there's another thing. If you start UML diagramming, in the end, you make a diagram with lots of arrows, and always in the end there is stuff that is really important, and you could not fit it in the model, or it's important and you want to say it. If you read this model, you should know this, and that's why you have comments. So here you have a class, and if there's something really important you want to discuss with the diagram, you put it in a comment box, and then there's this dash line, and you can use natural language for that. And please use this, because otherwise UML with diagrams become unreadable. I see I have 3 minutes left, and then it's the end of the lecture, so I'll do my best. Constraints, there are some kinds of commands. They are constraints, and you put them between these curly brackets, and you can put them in natural language or OCL, which is a object constraint language. This is part of UML and sometimes useful, and Peter van Oostrum will have a full course on that. So I'm not going to discuss this anymore. You have 4 kinds of constraints: invariants, preconditions, postconditions, and guards. And most of the time you use invariants, and those must always be true. So here we have an example of OCL. If you have a cadastral database and you know that all the parcels are bigger than 5 square meters, then you can say, in the context of a parcel, there is an invariant. It's called minimum area, and the area of this object is bigger than 5. Yes, I see a question. I'll answer it in the next 1 minute. And here you have parcels must have an owner. Well, it's also a constraint. Then if you have really big diagrams or big models like this Inspire project, you can group your classes into packages. They are a rectangle again with a small rectangle on top, and you can say this is in a package. So these 2 classes, they belong together, and this is an extra way of clustering or structuring your model. And then you can make also a relationship between packages, and it provides a higher level of abstraction. Here you have a package diagram of the Inspire project. So you have administrative units, that's a package, and it all has all kinds of administrative unit classes, and they are related. So this package depends on this package because there's this arrow, but not the other way around. And so you have package diagrams, they show dependencies. Oh, I need more than the 1 minute I thought I needed. So if you don't mind, I continue with just a few minutes so you can make your assignments on Wednesday. I'm sorry about it. I have to do the stereotypes. Stereotypes extend the semantics, because what always happens, you have a UML diagram and you want to discuss more than fits in the UML diagram. And then you could extend the UML language with stereotypes. And then you have a class, and above the class you have this stereotype and these brackets. and you can make special classes with special meanings. And one of the things is you can make code lists, for example, or enumerations. So if you have a code list, this class doesn't mean that structure type has 5 attributes, saying point, polygon, sketch, etc. But here, by saying this is a code list, then you say, well, this is sort of list of possible values for another attribute. So if you see code list, then you know, or enumeration, you know this is possible values, and that is done by doing this stereotype. And then in Inspire, this project that was used and that you could use, there are 3 stereotypes that you have to understand. One thing is called, if it has something as a feature type stereotype, it means this is an object or a class you can draw on a map. Voidable, we're going to discuss. I'm going to discuss that in a later slide. And there's placeholder, you don't see them anymore. They were used during the project to say, well, this class will be replaced by a real class in the future. I'm going to push forward till I see the final slide. Oh yes, we're really there. This is the final real slide. What happens a lot in this Inspire project or in UML modeling, that you know that a characteristic has a property in the real world, but you don't have it in a database. It's like, well, if you look, if you have a database with street names, it turns out that some member states in Europe, well, all the streets, they have 0 or more names in Europe. And so what you model, you could model that by saying, well, a street has 0 or more names. But then it happens that some member states of Europe, they do not really have the names of the streets in the database. So even though a street does have a name, it's not in the database. So to distinguish between the 2 cases, like saying, well, I know there's 2 cases now. If you give a street without a name, what does it mean? Does it mean this street does not have a name, or does it mean I don't know the name of this street? So for that, there is this voidable attribute introduced, and now it happens if you give a street in Inspire project and you do not give a name, then you know this street does not have a name. And if you, in exchange, you give if the attribute is voidable, then it's then you could put the value void there, and then you say, I don't know whether the street does have a name or not. So there's this distinction between I don't know, it has a name in reality, but I don't know it. Then you say void, and I don't know the name. I know this does not have a name. Then you just put no value there. So there's a subtle difference that you see a lot. So if you want stuff to have no value in the database while it has a value in reality, then you get put this voidable there. You don't have to do this for your exercises. Okay, well, actually now you know enough to discuss or to understand this whole UML diagram, and all the words are you can understand now. And definitely, it used to be the case that on every exam there is this question about I give you a UML diagram and then ask questions about, are these 2 objects related, or can a condominium be part of an administrative boundary? And then you have to say, look at the arrows and understand them and explain it. So this will, I think, will also be part of the exam this year. And now for the question. If you do your exercises, you have to draw UML diagrams, and there are different UML modeling tools. I'm using Enterprise Architect. It's really nice. It makes really nice diagrams, but it's a bit complicated, the tool, and it takes some time to get used to. And if you do not many projects, then you could also use easier tools. This Violet UML editor is nice, and there's also drawing tools like draw.io that lots of people will use. And the difference between the tools is that if you use Enterprise Architect, then you can then the tool understands your model, and then you can push the button and create a database table or create your Python program. And the other tools, they're just a drawing tool, so it looks nice. For humans, it's okay, but the computer really doesn't understand what you're doing. So for big projects, Enterprise Architect can be used, and as far as I know, you can use a 30-day license, so you can test it out for your assignments on Wednesday. But otherwise, you can always use one of the other tools. Okay, that's it. If you want to have a look at UML diagrams, you could look at the ISO website or the Inspire website. And well, this is how this diagramming tool looks like. I think I'm going to show you on Wednesday, give a short show of how you could use such a UML tool. I see a question. Visio is definitely okay. Lucid Chart, I don't know that tool, but in this assignment, I grade for the diagram and not for the underlying model. So if the diagram looks okay, the screenshot of a diagram, the tool is fine for me. Okay, well, that's it for today. Hope to see you on Wednesday. I'll stay around till 4 o'clock for if you have any questions or remarks or so. And otherwise, see you on Wednesday or next week or at the end of the week on Friday. And then we're going to start with SQL programming. Okay, see you around. And thank you.